Welcome to Ask and Learn.
So they want us to verify what they say in example 8 about z plus cross z plus being a well-ordered set using lexicographic ordering. Well, for something to be well-ordered, we need three things. We need one, our set to be a poset. And I don't know if they exactly state this anywhere in the chapter, so I don't think we can just assume it. Now, for the next thing, we want to show that our ordering is a total ordering. And then for 3, we want to show that for every S that is a subset of Z plus cross Z plus, and S is not the empty set, that S has a minimal, or not minimal, a least element. I guess technically it does have a minimal element, but more exact, it needs a least element. All right, so let's go ahead and start. So proof. All right, so a statement I'm going to use a couple of times is this. So instead of writing it out, I'm just going to say star and write that down. So this is from example 7, which I feel okay using since this comes before example 8. So this says that z plus with the standard ordering is a well-ordered set. All right. And thus it is a poset. Okay, so we have that statement there. Now, the first thing we want to show is that we do have a poset. Well, we can actually cheat a little bit and use number 37. So if you haven't watched number 37 or done the problem yet, you can go and watch that one, and we walk through the steps there. But we can use number 37 to help us with this. So we know that since z plus z is a poset, that z plus cross z plus with the lexicographic ordering is a poset too. So we're done with that first one. That's nice. Now we want to show that our lexicographic ordering is a total ordering. All right, so 2. So what we want to show is that for any two elements, they're comparable. So that's what it means to be a total ordering. So we're going to let AB, CD be elements of Z plus cross Z plus. Let me write that a little bit better, cross. So now, by star, so we know that either A is less than or equal to B, or B is less than or equal to A. All right, so we're just going to suppose that A is less than or equal to B. All right, so we have two cases. So case 1, A is not equal to B. Thus, AB is going to be less than or equal to CD. And then case 2, we have A is equal to B. Thus, we need to compare B and D. Oh, actually, this shouldn't be A and B here. Sorry about that. This should be A and C. So C, 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 because we're comparing these first two elements there. All right. So now in the case of A is equal to C, thus we need to compare B and D. And again, by star, B is less than or equal to D, or D is less than or equal to B. So just assume B is less than or equal to D, which then implies, again, that AB is less than or equal to CD. Thus, all elements are comparable, implying our ordering is a total ordering. All right, so let's go back up and check that one off too. Now, we need to show that for any subset of Z plus cross Z plus, that there is, or that is non-empty, that S has a least, oh, I don't know why I didn't say least element here. All right, so let's go ahead and do that now. All right, so what we're going to do is first let S be an arbitrary subset, and we want this to be non-empty, so not the empty set, of Z plus cross Z plus. And now what we want to do is create a set where the first position is going to be less than or equal to every other position in there. So we're going to now define a set A equal to, so it's going to be all the points x, y, such that x is less than or equal to z for all z of the point ZA. So, oh, and ZA is an element of S. Okay. So essentially what we've shown here is that if we were to take the complement, so if we were to do like C minus A, anything in this will be larger than our set A. So just kind of keep in mind that that's what we kind of did. All right. Now, let's see what we can do from here. Well, we want to somehow get a least element. So why don't we look at the least upper bound, or the greatest lower bound for the set A. So let's see if we can get something. So let's just go ahead and call this the point A, B. So we're just going to say that this greatest lower bound of A is AB. And now we'll go ahead and explain why we can do this. Okay, so let the greatest lower bound of A be AB. So we can say this for the following reason. Well, we already know that for all A, or actually, so in our set A, so in A, all of the first positions are the same. So what that means is when we do our ordering, we need to look at the second position. So let x1 y1, x2, y2 just be arbitrary, or so again, what we would do is, I don't know why it's not letting me erase. Oh, there it goes. So maybe a better way to say that is, so if all the first position in A are the same, then the second position must have a b less than or equal to y for all y such that xy is an element of S, since, or instead we can just say by star. So by that statement star, because Z plus is well ordered. So that's why we can go ahead and say that there is a b that's less than or equal to everything else. And then a b would be less than or equal to xy for all xy element of A. Okay, but we didn't care about A. We care about S. Well, if xy is an element of S, then AB is going to be less than or equal to xy, since either xy is an element of A and GLB of A is equal to AB, or xy is not an element of A, which implies that x is going to be strictly less than, or other way around, A is going to be strictly less than x, which implies A, B is less than or equal to x, y. So now this implies that AB is a least element. So, and that's what we wanted to show. Just double checking. So we showed that it was the least element, and so that was the last thing we needed to do. So we can go ahead and just kind of wrap this up by saying, since Z cross Z, or Z plus cross Z plus with the lexicographic ordering is a poset, the lexicographic ordering is is a total ordering, and we have that for all S subset of Z plus cross Z plus, S not the empty set, that S has a least element, we can say that Z plus cross Z plus with this well ordering, or with this lexicographic ordering, is a well ordered set. So now you can put your little proof box and the smiley face because you're glad you're done with it.